So now we want to approximate this exact relationship, this relation between the fine scales and the coarse scales. And let me make a small alteration here. I'm going to say this is minus the residual. It's just a matter of definition. So that means also we have minus the residual here. I think that's going to be slightly more consistent with what I've done before. And as I've also stressed in the previous video, in effect what we're really interested in is not trying to approximate precisely this step, but more explicitly the step of obtaining a true interaction with respect to the coarse scales, and that was this bilinear form acting on the fine scale solution, coarse scale test function. So that is what we're actually interested in. Okay, but we'll show that we actually have to make approximations to both of these steps to get something useful. So how are we going to proceed? How to proceed? Well, we're going to have to make certain simplifications and in some sense also approximations. And we'll make these simplifications and approximations under certain assumptions and also with a certain objective. And we will make the assumption that we are using the H10 projector. Well, that's fine, right? That's what we said was a good projector. So we're going to, let me state this differently. I'm going to focus on the H10 projector. Yeah, come on. Focus on the H10 projector. And I'll make modeling approximations that are consistent with the one-dimensional case. So at some point I'm going to have to introduce approximations, and I'll make the approximations in such a way that we're consistent with 1D. So modeling approximations consistent with the one-dimensional So what do these two things mean? Well, we looked at the one-dimensional case and we looked at the H10 projector, and we noticed some interesting results. Three, in fact. First of all, the H10 projector itself immediately meant that the fine scales are 0 on the element boundaries. Now remember that we said that if we take an arbitrary solution, we take the H10 projector, then our coarse scale approximation is going to be nodally exact. And the nodal exactness means that, well, at these points, our fine scales, which is the difference between the true solution and the coarse scale solution, is going to be equal to 0, right? So on the element boundaries, we have u prime is equal to 0. Then secondly, if we make, and this also is specifically in the one-dimensional case, so actually these both have to be taken into account for this to be true. The second property that we have if we take the H10 projector and the one-dimensional case is that the fine scale Green's function localized perfectly to each individual element. So localization of g x, x hat to k. Yeah, it's going to localize to the element k. And thirdly, there was sort of, I didn't explicitly point this out, but it comes down to the top ones as well, is that also the fine scale Green's function is actually 0 on the element boundaries. So we have g x, x hat is equal to 0 on partial k, yeah, in terms of x. Yeah, so this localization and also this last property should be interpreted in terms of x. So for x in k or for x in partial k. Actually, for the second property, localization, these are connected, right? So if x hat is in k, then for any x outside of k, it's going to be equal to 0. Let me show this again in my picture here. Right here. And so if x hat is in some element, and then for any x that is outside of the element, we get a 0 value. And only for x is inside of the same element as x hat, do we get a non-zero value. Okay, so these are the three properties that we'll be using to approximate both of these results boxed in red. And again, these are based on, these are properties that are true if we use the H10 projector in 1D. And we're going to use these as approximations for a multidimensional case. Okay, so let's first talk about this closure relation between the fine scales and the coarse scales through that residual. So we had u prime as a function of x defined, or sorry, as a function of x hat defined as the residual gx comma x hat, and again this was the weak residual for some UH, and I chose to introduce a minus here. So how was that defined? Well, this is going to be equal to, and let's focus on the advection diffusion equation now. So we get f as a function of x, gx comma x hat, and this was an integral over dx. So I'm just filling in the bilinear forms and linear forms that we would have, right? So I'm working out this now. Plus I'll go one step slower. The true definition is this is on Aleph omega. UH A dot gradient VH. We've substituted the Green's function, so we get gx comma x hat. And then lastly we have minus integral over omega of kappa times the gradient of UH dotted with the gradient of gx x hat. Again, these are integrands over dx, and also these operators, they all act on the x variable, right? So we have x's here. We should also interpret this one as a function of x and this one as a function of x. Okay, so now we're going to use this localization property, and we say that apparently we're taking into account u at the location x hat, and now we're going to take the element in which x hat is, and then we can simplify these and replace them by element integrals. Okay, so now we've used this localization strategy. Now, I don't quite like the way that this is written. We're using still the weak residual. I'd like to move this towards the strong residual. So we're going to do integration by parts now. And since we're integrating now only on the element domain, I'll get, again, element integrals, but also element boundary conditions. So what happens if I do that? Well, I get the first integral, right? Over k times f x g x plus, or now that becomes a minus, integration by parts, minus a dot gradient uh g x hat plus k kappa gradient, and this becomes now a Laplace operator. Times gx comma x hat dx. Okay, and I should be getting boundary values as well, right? What kind of boundary values would I be getting? Well, this one should give me a dot n times uh times g. But we know that g is equal to 0 on partial k, right? So this one is actually going to be equal to 0. And what boundary value would I be getting for the second term? Well, I would get minus partial k times kappa gradient UH dot N times G x x hat. Well, same thing. We know that G is actually 0 on the boundary. So this is also going to be equal to 0. So this whole term, right? So this one is actually 0. Okay, so in effect we only get the volumetric integrals, and we can actually write this in quite a nice form, right? This is going to be equal to k of fx minus a dot gradient uh of x plus kappa Laplace operator and all of that is going to go and multiply with our fine scale Green's function. The fine scale Green's function, right? Oh, mistaken, forgetting to do that all the time here. We're dealing with fine scale Green's functions. And this one is precisely how we defined our strong residual, R. Okay, so in fact we can replace our weak residual with our strong residual under the assumption that the fine scale Green's function is equal to 0 on these boundaries, right? Else we would not be able to do that. And also under the assumption of this localization. And that's why we're getting these element integrals. Okay, so that's nice. Now we can obtain u prime at some location only by performing an element integral rather than performing a complete global integral. Okay, so that was the first part of the story. Now we're going to have to focus on how it actually ends up showing in the finite element formulation. That was through this term b. So let's write out what that term actually says. Well, it kind of depends on how we obtain this formulation, but I'll go with this form. And when we've performed integration by parts, so then we get a u prime times a dot gradient vh plus the integral of kappa times the gradient u prime and dotted with the gradient of vh. So now, of course, I'll be able to write this as a sum of integrals. So I'll do that already immediately right now. Sum of integrals over elements. And with this second term, I would like to do something else. I'm also going to do integration by parts here. So that gives me minus the integral over u prime times the Laplace operator on VH. Now, why am I doing that? Kind of for two reasons. First of all, because I want to be able to get these strong residuals, these strong differential operators in there. Secondly, because we're developing a model for u prime and not for the gradient of u prime. And as you can probably imagine, it's going to be easier to get integrands, weighted integrands and sort of averages of u prime rather than averages of gradients. You can have small averages of u prime but still have large gradients if it oscillates a lot. So we expect this u prime to be slightly more well-behaved, more easily implementable, or it's easier to take into account the average of u prime than the average of its gradients. Now this should again give us another boundary integral. And sorry, I'm doing this on the element, okay, and then I'll perform integration in parts, so this is the second thing. And then I would get a boundary integral on the element as well, but vh dot n, but we will make the assumption that u prime is equal to 0 on the element boundary, again, based on the H10 projector, and based on this is again an assumption, approximation, and that's going to be consistent with the one-dimensional case. In 1D, this is not an assumption, this is a fact, and it will be true. In multi-D, this is not true, but we'll use it as an approximation. So we'll say this one is 0. Okay, so again, I can simplify the notation a little bit here, and you would get minus, no, not minus, I would simply get u prime times the adjoint operator acting on VH. Yeah, remember the adjoint of the Laplace operator, or the adjoint of minus the Laplace operator was minus the Laplace operator. the adjoint of a gradient was minus the gradient, so that's why this minus is coming from. Where this minus is coming from. And this one was already there. It's also there in the strong form. Okay, so now we have a simplification of u prime at x hat, and we have a simplification of how that's going to end up showing in our finite element formulation. So let's combine these two. So which two are those? That is this one. Can we see that? Oh yeah, actually. And this one. Hope that's visible. It's visible on my screen. I hope it's also visible on your screen. So we'll combine these two, and then we have that the bilinear form that takes into account the scale interaction u prime vh is going to be the sum over elements. And I'm writing an equality. This is going to be an equality in the one-dimensional case with the h10 approximation, with the h10 projector. Else this would be an approximation, but I'll write it as an equality for now, just to emphasize that this is actually still exact in certain cases. Of element integral of u prime, well, we define that to be the strong residual uh times g, and now I have to start to be careful with these variables. I want to integrate. So my original statement said x hat, but I want to use my x later on for this integral here. Right, that's the integral that we're actually interested in. So I'll make this into a y. And I'm looking for u of x. So that means that my x hat here has become my x. I get gy comma x. And my integral is over the first variable, so I get dy. And this is an integral over x, or sorry, over the element k. And we're multiplying this by the adjoint operator acting on vh and integrating over x. So again, this is exact in the one-dimensional case. But it's also rather impractical. And that is due to the double integration. Now we're doing a double integration here, and we would actually need to know g precisely, and which we can obtain, g prime precisely, which we could, but it's again, it's just impractical. So let's try and go a little further here. What we're going to do is we're going to simplify. And we're going to use simplifications that are, again, exact in certain special cases. I'll just write it down, then we're going to talk about it. I'm going to replace this by, again, a sum over all elements. That stays the same. But what I'm going to do is I'm going to pull out this residual and this differential operator. And they'll end up showing like this. Okay, what just happened? Scroll up just a little bit. Can I do that, please? Come on. Why does it sometimes not want me to do that and other times I can? Let's see. Yeah, there we go. So, what just happened? I took the residual and I pulled that out of this integral. Well, there's multiple ways of interpreting this. I'm going to do it the right way. Okay. I'm pulling this all the way out of this integral. And I'm also taking this guy and also pulling this all the way out of the integral. Now, I'm not allowed to do that. I'm only allowed to do that if these are constants. When are these constants? Well, these are constants when my differential operator acting on my finite element approximation function is a constant, which is only for lower order methods, so P1, so P1 approximations. After I've done that, I have now my integral over k times g dy dx. So that is what this is. But I don't like the way that looks because, well, I'm used to implementing things as integrals and not as multiplications of constants with integrals. So after that, I'm introducing a new integral, which is sort of fictitious. And in order to do that properly, I also have to then divide by the magnitude of k. Now I'm putting that 1 over k towards this parameter because then I get a nice parameter definition here, and that's how I obtain this new integral. And after that I shuffle around my variables such that I end up with an integration on my original variable x, and these are just different variables. So I think that is the proper way of looking at this. I can also try and give a more intuitive way of looking at this. You can think of this as a homogenization of the true effect of the fine-scale Green's function, or as a sort of an average, an element average of the fine-scale Green's function acting on the residual and on the differential, the adjoint operator here. And so going through the set of steps rigorously to obtain this derivation, you understand that this is still exact under certain assumptions, namely P1 finite elements, but the lower approach where we simply say we're homogenizing, we're averaging the effect of the fine-scale Green's function is maybe slightly more intuitive. So just to state what I just said, this is still exact if the residual and this L star on VH are constants, which is if F is constant, right? The force itself needs to be constant because it's in the residual, and if we're using with P1 finite elements. Okay, but now I end up with an expression that is actually kind of nice to work with. So now we have a nice expression, namely a summation over elements of an element integral of the residual of the core scales multiplied by a parameter tau times the adjoint acting on the core scale test function. Now you should immediately recognize this as the general form of our stabilized methods, where we had a residual acting on or multiplied with a stabilization parameter times a differential operator, which could vary depending on the stabilized method acting on the test function. Yeah, so we obtain here a residual-based stabilized method, but now from a completely different perspective, namely the perspective of scale interaction, fine scale approximation, variational multiscale, and Green's functions. And the strength of this approach is that it now gives us a very clean definition of the stabilization parameter tau as an element homogenization, an element average of a fine scale Green's function there we go, dy dx. Yeah, so this gives us a very clear definition of our stabilization parameter. I feel like I've been a bit inconsistent with my residual again. Let me scroll back up. Yeah, so if I'm consistent with my previous notation, then I should probably call this minus the residual and this is minus the residual, and then this would also be minus. Okay, so now we obtain a residual-based stabilized method purely from the perspective of scale interaction with a very explicit definition of our tau. Still, this is not very practical. Due to the difficulty of the tau expression. So in the next video, I'm gonna try and motivate a different approach or a different definition of tau, which is an approximation of what we have here. Now, why is this not a practical definition? This function can become quite complex, as we've seen in the pictures, in the slides. And for multi-D, it also doesn't make or becomes even more complex, and also kind of doesn't make a lot of sense because we made already so many approximations about the localization and vanishing boundary fine scales that this definition kind of fails a little bit. So specifically for multi-D. So I'll make an approximation for tau based again on the one-dimensional case that we can also use for the multi-dimensional case, and ends up working very effectively. Yeah, but that's what I want to do for now. Motivate or derive a stabilized finite element method, a residual-based stabilized finite element method, purely from the perspective of scale interaction, where we now have a very clear understanding of where our stabilization parameters come from. And actually in the last video that I'll post today, we'll actually see that all the stabilized methods that we've seen can actually be rewritten or can be obtained from a rewrite of this guy. Yeah, so that's what we'll still have ahead of us. Approximation of tau and obtaining SUPG and GLS. Okay, see you in the next one.